Welcome to panel 3 on materials, devices, circuits, systems, and beyond. This is your moderator speaking. I'm Ulya Karpuzcu from University of Minnesota. I'm a computer architect actually, but I work a lot with device and materials researchers. And my interactions so far with distinguished members of this community have been a pleasure, such as Zafar, Mike here, Steve, and also Jianping Wang from University of Minnesota, who unfortunately couldn't be with us today, but who sent everyone his greetings. Also, unfortunately, one of our panelists, Dr. Kaustav Banerjee, couldn't make it due to flight cancellations back-to-back, actually. But hopefully we'll be able to entertain yourselves before lunch. So here is how we are going to start. We provided the panelists with this seed question just to get the discussion started. But before we start, actually, I cannot wait to hear about our panelists' perspectives. Okay, we are going to start with brief introductions, and of course, no one in our panel needs an introduction just for the sake of procedure. I'm going to start with our first panelist, Professor Michael Arnold. He's a professor of material science and engineering at the University of Wisconsin-Madison. There, he has directed the Advanced Materials for Energy and Electronics group since 2008. Professor Arnold graduated from UIUC with a Bachelor of Science degree in Electrical Engineering in 2001. He earned his PhD in 2006 from Northwestern University in Materials Science and Engineering. Professor Arnold conducted postdoctoral research at the University of Michigan at Ann Arbor from 2006 and 2008. Please welcome Professor Arnold. Maybe I will first I'm sorry. So then our second panelist is Mike Burkland. He has been with Raytheon in Tucson since 1999. He currently facilitates the identification and creation of technologies to support innovative solutions for Raytheon business needs. A primary focus is directing development of advanced microelectronics technologies through Raytheon's participation in SRC University research programs since 2015. From this history of engagement, several DARPA contracts have been awarded to Raytheon in partnership with academic researchers for further maturation of SRC research products. From Purdue University, Mike earned a bachelor's degree in physics and mathematics and a PhD in physics with a minor in quantum optics from the University of Arizona. Our next speaker is Russell McMullan. Russell is an AMD Fellow, Advanced Process Technology Pathfinding, providing present and future technology evaluations and performance projections for AMD products. Russell coordinates and participates in external process research such as SRC, BETR, VLSI, and IMEC. Russell's 33-year career spans technologies from 0.5 micrometer planar to current state-of-the-art nanosheet, and has included roles across equipment, process integration, and product engineering. Russell has 7 patents and 2 industry papers. Welcome, Russell. And finally, Dr. Jeff Vedder. Jeff is a corporate fellow at Oak Ridge National Laboratory, where he leads the section on advanced computing systems research. He's a fellow of the IEEE and AAAS. So welcome, Jeff. And now we are going to start with the perspectives and then open the floor for discussion. So, and our first speaker is Michael.
Okay, thank you. So I am a material scientist. So I'm going to do my best to answer this from a perspective of a material scientist from academia. So really, the question the panel we've been tasked with answering is how predictable will materials and device progress be? So with CMOS engineers working at the higher levels of abstraction in the system stack have had a predictable technology roadmap around which to design their solutions. Will the same mode of working be feasible with the new device and materials developments? If not, how could we rapidly develop complex systems using these new components? So I take that to mean as materials are being discovered more and more rapidly, how will system designers keep up? Okay, so I'm going to try to answer that from a materials scientist perspective. So firstly, from my academic perspective, I think industry looks to me from the outside like they've done a fantastic job of integrating, absorbing new materials already. And of course, there's very famous examples of copper interconnects, strand-in channels, hafnium oxide and gate stacks, low-K dielectrics, and et cetera. Before I get to giving my perspective on answering this question in more detail, I want to say a little bit about my research and my experience and my perspective and backgrounds. So my research focuses on carbon nanomaterials for microelectronics. I've worked on carbon nanotubes on the material science part and a little bit on the device part for, well, since the year 2000. And we've worked on graphene nanoribbon, HBN synthesis since around 2010. So today I'm going to talk about my perspective and experiences with carbon nanotubes in particular today. So carbon nanotubes are pretty amazing semiconductors, but how can we use them? How can we ever use them in an integrated circuit? This is what nanotubes look like when you make them. This is what silicon looks like when it's being used, obviously, in going into a fab. So they're pretty different. How are we going to go from this? This just looks like, it could be soot from a campfire. And actually, most of the material in this powder is not even carbon nanotubes at all. It is just soot. How can we go from this to something like this with nanotubes? So that's my job as a material scientist. Back in 2000, when I started working on nanotubes, here's what we did. We took this powder, we put it in a solvent, we ultrasonicated, which broke apart all the tangles of trillions and trillions of nanotubes in that powder. They were floating around, and we just would spin coat them onto a wafer. We would then put down electrodes for source and drain and use the backgate. And occasionally, a nanotube would cross between our electrodes, and we'd have horrible device yields. There'd be maybe one nanotube or bundle of nanotubes per transistor. And the other thing about this powder is that not only is there a lot of soot in there, but among the nanotubes, there's different types of nanotubes. There's metallic nanotubes and semiconducting nanotubes, and we want just those semiconductors. And so some of my first work on nanotubes was taking a bundle of nanotubes that had both metallic and semiconducting ones and using pulses of electricity, transistor by transistor, to burn out the metallic ones to get just the semiconducting ones crossing the channel. So back in 2000, the field was super primitive. Okay. But it's undergone really a huge transformation in the last 20 years. Now the field has really become much more savvy in terms of use of chemistry. We could take this heterogeneous powder and we could use surfactants and polymer wrappers that can wrap around the tubes helically, like shown here. And that wrapping could be highly selective. We could grab onto just semiconducting tubes, not the metallic ones. And we could even grab onto particular diameter ranges of nanotubes that have particular band gaps, all the way down to nearly single structure of nanotube. So that beaker on the right there, that's a beaker of the 6.5 carbon nanotube. It's 7.57 angstroms in diameter, has a band gap around 1.24 electron volts. And we extracted that. That purple colors from that 6.5 nanotube, we've extracted that from that black powder. Then once you have all your nanotubes floating in solution, you have to assemble them onto a substrate. It's easy to just spin coat that solution on the substrate and you get randomly oriented nanotubes, but to really take advantage of nanotubes, they're wire-like objects. You want them all oriented kind of like FinFETs, so you want each nanotube to be a fin, part of your channel. So how do you align nanotubes from solutions? So this is something we've worked on for many years as well. One really cool approach we're exploring right now is to form liquid crystals out of nanotubes. So the nanotubes are the liquid crystal element themselves. If you take those nanotubes floating in solution wrapped by the polymer, that's an organic solvent. That's the purple color there. If you layer that on top of water, the nanotubes go to the interface between the two solvents. And they form a two-dimensional liquid crystal. And the rods, so whenever you have a high density of rod-like objects, they align themselves. That's like what a liquid crystal is. So we could get the nanotubes to align themselves, then we could pull a substrate out to pick them up onto that substrate, and we can get very dense arrays of aligned nanotubes. So here, this cross-sectional TEM shows that a tube spacing around 3.5 nanometers. The AFM on the left is like a top-down view. It's not perfect yet, but it's really close to what we'd want for a transistor. And we've made transistors, and they're pretty nice transistors. Really high current densities, but we have a lot more work to do. So we can't yet achieve this uniformly in a 300 millimeter wafer scale, but we're getting closer and closer. So the progress has been dramatic over the last 20 plus years in going from this very basic single nanotube transistors that sometimes work with very low yield to now being able to coat 4-inch wafers with aligned arrays of nanotubes pretty uniformly that are mostly semiconducting. Okay, so getting back though to this question, materials are being discovered more and more rapidly. Can circuit designers, keep up? Well, I feel like a snail, or a turtle. Okay, so I've been working on this 20 years. So my question is, well, are circuit designers faster than turtles? I hope so. I hope so. Okay. So really, the nanotubes were discovered in 1991. And the first transistor from a nanotube was made in 1998. But we're still really struggling with synthesis, purification, integration problems. And these are not just problems unique to nanotubes. So nanoribbons, 2D materials, 3-5s, and silicon. Many new materials are plagued by the weakest link of the synthesis, integration, purification challenges. So my point of view as a material scientist trying to work on really cutting-edge new materials is that this is how the flow diagram is going. So new materials discovered, there's this one-off device demonstration, simple circuit demonstration. Then there's years of toiling on developing new growth approaches, new synthesis approaches. And then once we make a process that's going to work really well, we need maybe a specialized tool that could be integrated into the fab for this new material. And then once all that's done, then we can maybe see this new material in commercial production. And then in parallel, the circuit designers can work, but they have a lot of time, is my point. And so our interactions with industry say that even if we had a process for perfectly aligning nanotubes on a 300 millimeter wafer, and we had a tool for doing this, could go into the fabs, even if we had that ready right now, it still would be 5 years until that would be in production. That's what I've learned. But really hoping to learn more from the rest of the panelists, so thank you.
Thanks, Michael. And our next speaker is Mike, I believe it is. Yeah, I can find your. Hold on. There we go.
Okay, and is it, so advance with that one, and that's the pointer. Okay. Hello, good to be here. Thank you for the organizers for inviting me. I appreciate the opportunity to see some old friends and make some new ones. I've been with Raytheon 25 years, impersonating an engineer, but I'm actually a physicist. So far I've gotten away with it, but it's been a really interesting time being in industry. I also will explain a little bit of my academic career here, but seeing both sides of the fence and working with SRC, it's a very complementary combination. So, a long, long time ago, in a galaxy far, far away, I happened to be walking through the halls of the Physics and Atmospheric Science building, just a few blocks south here, on a May afternoon in 1990. And a fellow graduate student of mine runs up to me and says, "Mike, you've got to see this. We've just made an amazing discovery." And so I went to his lab, and he showed me a microscope slide with a brownish black smudge on it. I said, "Wow, Willis, you've really outdone yourself. I mean, it's been weeks since I've seen a dirty microscope slide." He said, "No. What's on there is a thin film of fullerenes." I'm like, "Ooh, what's a fullerene?" And he explained it to me. And I said, "Oh my gosh, you've got to give me this because I have a scanning tunneling microscope in my lab and we got to image this." Had our advisors been better friends, I would have taken those images there. Instead, the samples were sent down the street to the Optical Sciences Center, and they had an STM down there. I think the one on the right is the original one, but anyway, it was incredibly exciting time. And the great Don Huffman, the advisor who did this, had he been a chemist, he would have won the Nobel Prize, shared it with Richard Smalley from Rice in 1996. But it was just monumental, really exciting work. And as Michael pointed out, nanotubes came out about a year later, and they've been messing with SpaghettiOs and meatball conglomerations for quite a while, but obviously a lot of progress has been made. So that's kind of my roots of 2D or, well, very small 3D materials here. Just in case you're feeling sorry for me, I took this picture a few years later. I had a different advisor at this time, but we worked in the Lunar Planetary Lab and went to Mars and had an imager we built, and it was an incredibly exciting time. We went to Mars again after this on another lander. But this shows there's success in scaling, right? Nanotubes, Mars. So I've had a very exciting career. I won't go into all the Raytheon assignments and such I've had, but we've done some amazing things there. And the bumper sticker I have for workforce development that I try and share as often as I can is, if you want to make money, students, go work for fill in the blank. But if you want to make history, do what we do. It's incredibly fulfilling. It's addictive. It's adrenaline rush. You meet amazing people doing amazing things, and at the end of your life you will be glad you did it, and you'll have a decent bank account. But that's the lure, I think, for technology in general, but semiconductors. It's excitement. You're able to help change the world. But what I want to really kind of dive down into is how the defense industry absorbs technology, or how technology gets transferred into defense. And it's not it's kind of a random walk in a sense, and there's different types of stories, but I'll go through a few of them here. E. Robbie was part of the Manhattan Project for a while, but his big fame was he went back east and developed RF during World War II. And Raytheon had started in the late 1920s, but became obviously involved in radar, but it was kind of a serendipitous event where Percy Spencer, engineer at Raytheon, was working on RF microwave and found that his candy bar had melted in his pocket, and discovered, well, we can heat foods this way. So the radar range came out. Of course, this was a great commercial success, but it was kind of a little serendipitous with the government work. But the radar range and the commercial application, of course, didn't just stay there. We do great radars today, as you know. The other example, frequency hopping, and you may recognize this lady, Hedy Lamarr. Brilliant story. There's a great documentary on her on Netflix, but also Richard Rhodes wrote a great biography of her, but she was a genius. And she was Austrian. She was originally married to a weapons manufacturer in Austria in the 30s, and was at all these dinner parties and heard all these plans about, what Austria and Germany were going to do, and then came to Hollywood, but realized there was a need for secure communications for being able to guide weapons. And there was a problem with torpedoes being accurately guided to their targets. And she had the idea from a player piano, if you have the same tape on the transmitter and the receiver, you could hop frequencies and not get jammed. Of course, use this all the time in our communications. So she got a patent for it, working with her partner, who's a music composer. But as with all great ideas, she's trying to sell it, and the Navy was not really, they didn't get it, right? They didn't get it. And it took about 15 years or so before this approach was finally adopted. And she was, in the 1990s, recognized for her success in this area. But it was a long slog. But other examples of where technology was really championed by the government is in stealth. Of course, we have, and this is ancient history, right? F-117, we have a lot of stealth aircraft now. But this was championed by Heilemeyer, DARPA fame, who we go through all his questions. But this was a successful technology transfer championed by the government, but cost a lot of money to do. So there's kind of easy paths and difficult paths, but there's really not a good systematic way of introducing technology into defense. And that's been the biggest challenge in my career, is taking all the great stuff you guys do and selling it on my side of the fence. Because the amount of uncertainty, something that's new or different, there's a very high bar of risk. And I think the government's doing a great job in trying to lower that bar with the CHIPS Act and such. But it's still a bit of a challenge. So just a little bit more history here. This is a very interesting article. 10 years ago, William Lynn III was under Leon Panetta. And if any of you are old enough to know what the military-industrial complex was in the 50s and 60s, it drove microelectronics. We all know that. But he wrote this 10 years ago, where defense is a gnat flying around my Intel buddies' heads, you know, get out of my way. There's not the volume for us to be consequential in the driving of the technology. It's all being commercially driven. So, but in those 10 years, I think the country's getting in a better posture to bring technology into defense. But it's a tough it's a tough road, and we have very challenging problems. So thermal is the biggest thing we face. Unfortunately, it's a universal problem, and everyone else is dealing with it. But if you want to have a missile that will fly a long way because it's light, then you've got to have something that's power efficient. But if it generates a lot of heat, you got to put thermal mitigation technologies in there. That adds weight, it adds cost, reduces range, and before you know it, you've got a hot brick that you're trying to send, you know, X amount of miles, and it's you can only carry one on an airplane. So I'm very excited about what's going on in microelectronics to help really mitigate this problem. You've all seen this. I'll skip over this. Really, the non-von Neumann area is what I'm very excited about, except it's being applied to AI and ML. And forgive me, it's this heresy, but we have other computational workloads that are not AI or ML. I have high precision, high accuracy computations that I've got to do with non-von Neumann efficiencies. So I'm pushing really hard to try and extend capabilities into those realms. We have shown through DARPA Frank program that we can take MRAM and do, which if you apply it to in-memory processing, you can have very efficient computations in terms of energy, but the precision and the accuracy is still a challenge. So I think it's feasible, but it's not the shiny object. The TRL scale here, just to go over, you probably are familiar with this, but the Valley of Death is really what ME Commons is trying to get us through. It's the last part that is tough to get technology transferred into production programs. So making the value proposition and working with industry, that is really critical to get these technologies into your companies, whether it's Intel or TSMC or AMD or whatever, so that defense can then buy them. That's kind of the strategy I've been going to. So anyway, hopefully that gave you a little information you didn't have before, and I probably have taken more time than I needed to, but thank you.
Thank you very much, and let's welcome our next speaker.
All right, so first off, thanks to organizers and especially Zafar. You know, we connected at the SRC Tech Connect, so connection made. Thanks SRC. And I think yesterday we heard how unpredictable material breakthroughs are. We don't know if it's going to be carbon nanotubes assembly that gets solved, or if it's the TMDs, contact and dopings that get solved. And I think Alexander also kind of mentioned that you don't know what you're going to get and what you're going to find, and that's the exploration and research that everybody's doing. So rather than trying to predict the future, I'm going to go backwards and look at the kind of a little bit of a history overview. And I thought I was going to get the deepest reach back in the timeline, but Mike, I think you beat me. So this is only back to 1970. So I actually started working in 1990 on CMOS, and occasionally we run into these problems, and then we talk about, oh, it's just like a forward biasing the collector into the emitters. You need to go talk to these bipolar experts. I was like, bipolar? Why did anybody do that? And the answer is on this slide, and you got this from a VLSI presentation. And I try to get to the point down here. So bipolar was the core logic switch back in the 70s and 80s. And this little diagram, you probably can't make out much about it, but this is a thermal management solution. At the end of 1980s, it had a cold plate, it had a compression spring and helium cylinders that rested on the silicon. And so that was an industry solution to a problem dealing with thermal management back at the end of the bipolar. But of course, what happened? CMOS came in, 10x reduction, and 10-year great progress, right? And you'll kind of see that kind of timeline so if we can come up with a TMD material that gets us a 10x power reduction, which should be pretty close to that, that's the equivalent of a 10-year processing experience. So that's how much it's worth. Also listed some of the materials. It's not a complete listing of the materials. Accuracy is debatable, but really after CMOS plateaued in the 90s, this was, material science saved the day in the 2000s with strain engineering, right? The high K metal gates, the ultra low K dielectrics, the SIGGIs and SIPs for the source strain strains. So really they carried the day for the decade. And starting in 2010s, it's really the start of 3D scaling, right? This is when fins went vertical, right? And it's also when there were some departures, different products didn't go to the latest node because fins are basically the same, right? It's all engineering. And so we are getting good scaling. And scaling is great for packing more computations in for HPC, but not so great for analog to digital and power type of thing. So, that's when you saw some of the products staying on the older nodes. So, industry does identify, the best devices for the best application, and it does it through these technologies. Further on, the gate-all-around 3D, right? So this is more 3D. We're going into stacking silicon on silicon. The enablement of this is through the vertical interconnects. This is IMEC, and Raj, I saw your new one today. I'm going to try to capture that one as well. It's got in the nano TSVs. So basically, we have a full spectrum of pitch and size and densities. So we can make whatever bandwidth connections that we need to. It's all optimizable, but so that's all very configurable, right? Last thing is you can see that the materials at the end, these are speculative. Of course, we're not done with the decade, and 2030 is the next decade. But materials are getting exotic, right? So that is the challenge that we have in the industry, and thanks for your time here to let me share my views on that kind of challenge. All right, so Raj actually did a good job of stepping through a lot of these things on this chart, but I will try to point out a few more things, and it'll kind of relate to some other discussions. So as we saw before in bipolar and CMOS, but what you saw on these kind of product type dots, it wasn't a clean transition, right? It does take 4 or 5 years, even after something as great as bipolar to CMOS is identified for the industry to convert over. So that is about the implementation timeline. The second thing you see is that this power wall, thermal wall. It has continued, even though we got a brief reprieve for CMOS. So what was the solution, right? More things in parallel. But we still got the scaling, so we can start doing things in parallel. And that's where these core numbers started to tick up. All right, that worked pretty good. And we got some strain engineering, great. So yay, we got a little bit better single-threaded performance. But really, the industry has continued to scale on the multi-threaded performance. And maybe the easiest example of that is GPUs, right? GPUs that do things in parallel, they do it a lot, versus the CPUs are more single-threaded. Yes, but that eventually started going out of whack too. If you notice these dots, well, geez, there are less cores, less power. What's going on? Well, technology is slowing down, so designers are able to do different types of cores, right? So you can get a power efficiency core, and that's the lower dots, and you get a high performance core. And with the combination of 3D, now we're able to mix and match, right? So you can do this design on this technology, and the high performance on the one with the most drivability on it. And a very good example of what that allows, this is the, again, trying to get high bandwidth memory. I hate to say it, for machine learning AI applications in particular, the choice of memory makes a 10x reduction in the amount of power that's consumed, right? So that's equivalent, for that one case, it's an equivalent to 10 years worth of process technology development. So coming back to the question, basically we got three legs, right? We got the workload to consider, we got how the hardware can be optimized for that workload, and of course we got the raw intrinsic technology. And basically, as long as two out of these three are working, then we're going to make pretty good progress, right? And the abstractions are definitely needed to be able to handle. All right, I get this much memory, and I've got these chiplets to choose from. How to make the compiler work the best to be the most efficient. There still is a lot of opportunities there. But again, that's all one case at a time, and then the next case at a time. Whereas the process, if we get a breakthrough, when we get a breakthrough on the materials, that's going to make all the workloads more efficient, right? So that's what I had to share. Thank you for your attention.
Thanks, Russell.
Very good, thank you. There we go. Well, good morning, everyone. Thanks for the invitation to speak. It's been a very informative meeting so far. I think Mike made the biggest controversial statement so far when he said 1989 was ancient history. So we might have to start with that one in a moment. So let me dive in. So why am I worried about this area? I'm not a materials scientist. At DOE, we have a lot of large facilities, many of them billion-dollar facilities. I'm in computing, and so we're focusing on the next generation systems. And so this includes things like Frontier, which is the system that's just been installed at Oak Ridge recently. It is the nation's first exascale system. One thing I want to note from this slide is that around 2010, we were using multi-core. Since then, we've transitioned all of our systems to large GPU systems. And so if you look at that, we have a system that has 74 cabinets. It's got almost 40,000 GPUs in it, 700 petabytes of storage, including some non-volatile storage, and it's number one on the energy efficiency list as well. If you look at it, it's impressive. Just if you think about the physical characteristics of this system, one cabinet weighs 4 tons, right? Because almost everything in the system is liquid cooled, including the memory, the NIC, the GPUs, and the CPUs. It has a lot of wiring. It's got, like I said, a lot of memory, and it's an impressive mechanical engineering feat. So energy efficiency, we believe, is going to be the main driver going forward. If you look at this slide from Jack Denguer, it talks about going from teraflops to petaflops to exaflops and what the rough order of magnitude in years is for that. We see that extending. That's for a number of reasons. Some of them are technical and roadmap related, but if you think about it, any zettascale system that we're pondering right now is going to need about 1,000x improvement in energy efficiency. Now that's a heavy lift because you can't just make one thing more energy efficient. You have to make all of those major components more energy efficient. And as I mentioned earlier, domain-specific computing is the trajectory we're on right now using normal CMOS. But we think longer-term responses will need a new paradigm, and that is things like you heard about spiking neural networks and analog computing and some other areas like that. So that's what I'm going to just quickly go into to answer this question. And I will just give you a very quick overview of a project we have at Oak Ridge called Abisko, and it's a microelectronics project. Now, it's not just a microelectronics project, it's a microelectronics co-design project. And the real point here is to try to understand how you do deep co-design, thinking from the very high level of algorithms all the way down to materials. And this has been emphasized in both the DOE reports as well as more broadly in the community. So in this project, as I mentioned, we are going up and down the scale. We have people on the project that are in all of these areas. Our focus for this project is to design a spiking neural network chiplet that can be integrated on a contemporary system. We can use that chiplet to explore new types of materials. Some of them were mentioned earlier. Memristors, we're looking at tantalum oxide, as well as EC RAM, electrochemical RAM. And then we're trying to figure out how to put together a kind of a design of how this would work. The application we're looking at is CERN. We already heard about CERN this morning. If you see that device up in the upper right-hand corner, that is, there's a little red dot down near the x-axis. That's a person. And so it's a major instrument going into CERN. It needs, it has pixel detectors in it. These are called smart pixel detectors. The clock rate is about 40 megahertz, so they easily generate petabits of information. Right now, it's all digital. And so what we're proposing is looking at an analog mixed signal implementation that does a lot of that filtering before it ever gets converted to digital, in hopes that we'll save power, maybe improve performance and accuracy. The algorithms team is taking that data that we have, particle charge clusters, and coming up with a SNN formulation. In that SNN formulation, we now surpass our normal neural network, digital neural network implementations, and can get that down to about 400 neurons and a few hundred synapses, I believe. But that work is very important, because later when we talk about the crossbars and how this fits together, you need to know what that spiking neural network is going to look like. Software, we are doing a lot of work in software. There is a big challenge there. I think going forward, that is going to be something that we all need to spend a lot of time on. It's even for something like moving from an NVIDIA GPU to an AMD GPU costs hundreds of millions of dollars for a lot of applications. The architecture work is, as I mentioned earlier, focused on chiplets and a RISC-V implementation. The idea is that we have this neuromorphic chiplet that has many clusters in it. The clusters can be focused in on here, where they show you the actual crossbars that were mentioned earlier. We do have some of those crossbars and are designing these infrastructure components to go around that crossbar. This particular one's EC RAM, and it gives you the matrix vector products that we heard earlier. And that's basically how we're going to formulate the spiking neural networks for this particular application. And that's, again, the EC RAM, which we didn't hear a lot about, but it is a 3-terminal device, and there is some hope that it's more programmable at a finer granularity than the memristors, and solve some of the variability problems that we've encountered there. Finally, down at the devices and circuits level, this is where we actually have to come up with new formulations of how these devices are going to work, measure them, understand what their characteristics are. We've built a few prototypes and have them at Oak Ridge, and have been testing small crossbars with EC RAM. We're testing things like the conductance granularity and the distributions, trying to understand if this is something we could actually deploy at a site like CERN and have it there for the lifetime of the system. And there's a lot of open questions there, as we've heard yesterday and today. So at the bottom level, the hope is that the materials team that we have can look at the actual materials themselves and try to understand if there are ways to correct for some of the problems that we're seeing. The team at Oak Ridge is using microscopy to really dive in and understand how memristors are formed, and actually at the atomic level, how the vacancies are created, things like that, so that they may be able to tweak them to get around some of the programmability and durability problems they have. And so just to wrap up, I went back and populated this chart with the interfaces that we have to deal with. And so this goes to the question on the panel about how we make this easier. And I believe part of it is to try to come up with tools that we can use to span this hierarchy of abstractions that you see here. And we all know about compact models. And then there are, PDKs with a lot of information in them. You get up to things like ISAs and intermediate representations, and then even up to APIs and motifs. Those are things that we're focusing on in this project and trying to understand, if there's some convenient ways we can jump across those boundaries. And then just for full credit, going back to the question, I put a couple answers in here. The first one is open modular tool chains for innovation. I've spent a lot of the past 20 years managing teams that do software work. The availability of tools like LLVM have been phenomenal in both workforce development, in innovation, in portability. A lot of companies have given up their proprietary tools just because LLVM is more economical for them to build on. We need that in this area. And then there's the vertical integration toward end-to-end code design and design space exploration. I think when we start looking at all of these tools and kind of aligning them in a vertical stack like I just showed you, there is a real impedance mismatch between all of those levels, and you have to have people in there doing a lot of manual work. And it would be nice to have a more cohesive vertical integration of those tools. And then finally, just the interfaces among the components. Obviously, there are things like TCAD and Verilog A, but down at the materials level, they really do still just use a lot of plots and other things that describe what they're seeing, and it would be good to have that be automated as well. So with that, I'll quit. Thank you.
All right, now we are opening the floor for questions. Okay.
Thank you. I have a question. So when you look at the different levels, at the top level, where do you see like a modulars that you can use more generic models to using AI or machine learning to push them?
Yes, so one of the things that we've observed in computational science is just there are libraries, there's motifs that people use, there's frameworks, and in the AI community there are things like PyTorch and others that go a long way towards solving some of these problems, but they really need to be reformulated and mapped onto these new architectures, and sometimes the infrastructure isn't easy to map on a new architecture, and so we've been learning a lot of lessons there in how to do that mapping. Does that help answer your question?
Yeah. So maybe let me ask another question. Sorry,
Sure.
Second question. So when you move from PDK up, and then of course top down from the high synthesis level, and then where you can use the AI. So in the middle, that particular location where you do the interface.
Right.
My understanding is that interface depends completely how modular each module were defined, functionality.
Right.
Because otherwise, when you push down from the top level, once you change to a different, like a manufacturing location, all the PDKs are
Yes.
changed. You cannot inherit the top level
Right,
of the
right.
generic model. Thank you.
Yeah, and that's where there might be an opportunity. If you look at some of the new tools that are out there, I think there's an opportunity for this. LLVM, for example, has all the languages get compiled to LLVM-IR. And so once you have a front end, whether it's Julia or Fortran or C++, it all ends up as LLVM-IR. And then all the optimizers you write for that do constant folding and things like that, they just work on LLVM-IR. And then there's a back-end phase that could be proprietary that maps it to the GPU, the specific GPU or CPU that you're targeting. That would be something that, you know, I think would be a huge opportunity here. Now, there's proprietary PDKs and things like that you have to work around, but I think that would be, you know, be a big advantage. And this is Silicon Compiler. I mentioned them. They're a company that's trying to do some of this right now. Yours is.
Okay, I think I got it. Yeah, I think at every level of abstraction, there's some efficiency loss, and it kind of triggered on your AI machine learning aspect of it. If we could really get a good database and see where those efficiency loss are being gained or you know, made better, then you know there might be some automation ideas on how to optimize the abstractions that are used instead of using LLVM. Maybe use a different compiler for certain different cases.
Hi, this is Gil Vanatop from Intel. One of the things, I volunteer for a group that does studies for DARPA to look at, you know, what are areas that, you know, maybe they should be exploring. And one of the workshops that we're doing is in this space. It's like, well, can you know, machine learning accelerate process development, right? Materials development. And so we're going to have a workshop, and so we haven't answered that question for ourselves. But while we were doing this study, you know, Google published a paper where they discovered like thousands of new materials, right? And then at the same time, I think it was a Berkeley group published a paper of validating, you know, that they could create all these different materials. So we looked at that and we're like, wow, this seems like a leap forward. But then a few weeks later, a friend of mine from Cornell forwarded me a critical review, not of the simulation part, of the discovery part, but of the demonstration part, that really, okay, that, you know, those materials hadn't really been proven. So my question is like, so it still looks like, you know, discovering them theoretically can be done very, very quickly. You can't use traditional, like, well, large language models to accelerate process development because the databases are actually pretty sparse compared to these other fields that you look at, right? And even the data that you have, you know, you don't really, it's all different, right? It's not standardized. So what are your thoughts in terms of the ability to use different types of machine learning to accelerate, you know, engineering progress?
Yeah, I think that's a great observation. So, yeah, materials genomics and machine learning and so forth I think is a really tremendously effective way for discovering new materials, especially screening among like a materials system in which there may be multiple components, maybe four element systems. You could, you know, screen through many different compounds, find the compounds that have the properties you want. But the challenge is, as you say, is how do you process it? How do you synthesize it? How do you make it? I don't have a good answer for that. I mean, so I've been, as I mentioned, working on one material for a long time, and I just try to use creativity, my students' creativity, and the process of invention. So I think, can we get generative AI to replicate that? I don't know.
I'll just comment. This idea, I've seen a couple papers recently that talk about using large language models to do meta-studies across all the published material about materials, and they can suggest experiments. They may be nonsensical, but you know, you might be able to filter those out somehow. One of the things that is going on at Oak Ridge is a real priority is automating the lab experiments somehow. And you know, one of the fun things you can do with something like ChatGPT is upload a paper to it and say, what's the scientific hypothesis of this paper? And it'll give you a hypothesis. And then the next question you can ask is, generate an experiment to test this hypothesis. And then it can actually, you know, give you some ideas there. Again, it's not reasoning, it's just associating. But you know, sometimes that gives you insights you didn't have before.
Sure. Sammy Tin, Department Head of Material Science and Engineering here at the University of Arizona. Fantastic panel, and I'm really, really glad that we're having this discussion. So, as much as I hate to admit it, it seems that innovation in semiconductor manufacturing is more than just about the materials. It's also about, you know, the design, architecture, the processing, the software that's really driving some of the hardware designs. So being at a university, we're very good at compartmentalizing people in terms of training and education, right? You're a physicist, you're a chemist, you're a material scientist, you're an electrical engineer. So my question is, you know, it seems to me that, you know, to really move the needle in terms of innovation and addressing a lot of the workforce needs for semiconductor manufacturing, really start thinking about, you know, creating perhaps a more holistic educational program to support the community. I mean, you know, Todd's talk yesterday, he very clearly mentioned that ability trumps skills and knowledge, right? So, I mean, what are the thoughts of the panel? I mean, it seems to me that the ideal person to be working in the semiconductor manufacturing industry would have, you know, a electrical engineering degree, a computer science degree, a material science degree, a systems industrial engineering degree, but that person doesn't currently exist.
Yeah, so that's a great reason why a semiconductor career is great. You can do anything that you want to, and I absolutely agree, right? There's, we make design choices and architecture of, you know, we talked about drivability, I think, at the dinner table last night. You know, so some devices have better drivability for some power applications, whereas, of course, you know, the minimum amount of drive to do the switch, the lowest amount of energy, that's the best thing for computations. So sure, taking an understanding of that and breaking it down further, you know, the contact resistance is a huge problem for TMDs, but it's also a problem for me. I didn't go into too much in the history, but we always work with nickel silicide, cobalt silicide, and going forward to the nano TSVs, the solving that interfacial material of the resistance right next to the power source is a big benefit if we can improve that. So I guess I agree that all those things need to be considered, and it all plays in together, because ultimately we're just trying to make better performance. That means better, quicker, cheaper, less power calculations.
Any other questions?
Well, Sohail Salehi, EC faculty here at University of Arizona. I kind of wanted to share some thought about the great insights that the panel shared, and also ask a question. So there was a conversation about AI, and what I think about when I think about AI and using it as a tool is it reliable? Is it secure? Can it be fooled? And we know that these are all possible. There are a lot of papers coming out how you could, you know, do adversarial attacks on these machine learning. And it's not just the algorithm. It goes across, right? The architecture and the circuits, and even we are showing in our research the device also could be attacked that could affect the application level accuracy to drop significantly. So now, as long as we're using AI as a black box without any interpretability or explainability, I find it really hard to believe that that's going to take over in terms of designing for us without human intervention. You know, as you said, they're using large language models to do all of that, but we know the flaws. It's a new technology, it's a new tool. There's still a lot of research happening, finding the flaws of it. So I don't know the maturity of it. It's there to be used as a tool. So that's my thought on that. But also in terms of, some of the presentations showing the AI for high-performance computing. So these are modular designs, right? So you design one module, you replicate it. Again, from the security perspective, reverse engineering is a tool that we see time and time again being used against us, against the chip designs, the IP stealing. And one of the things is I reverse engineer one module and I can replicate the whole design, right? And that's something that's not being considered, I feel like, in the design process. Any thoughts on that?
It's, yeah, I'll
Yeah, first, obviously, you commented AI, it does have some fallacies. As far as the ability to go reverse engineer a single module of like a GPU, I would just say, good luck. It's these RTL implementations and everything, even small differences from cores to cores. I mean, I don't know. Maybe you have better examples of you being able to detect, deconstructing a whole module design. But I haven't seen that. And we look at competitors' parts and try to do this too, and it's pretty difficult. Yeah.
What I meant was not like necessarily the GPUs, because we're talking about hardware accelerator design using emerging devices and technologies, where we have this crossbar that we are going to use for a lot of the operations, the vector matrix multiplication, right? And the architecture stays the same because the operation is the same. Not necessarily a GPU, the RTL level code, but what I meant was more of the crossbar architecture.
Sure, I think you could reverse engineer some of the small architectures. Yeah.
One ingredient, I think, for people to reverse engineer is kind of intuition. They kind of know what to look for. There's some anecdotal stories I've heard of designs that are generated that just look like they're crazy, they're nuts, but they do what they're supposed to do, and they're not intuitive. There was a recent story I heard about a drone flying alongside a manned aircraft, and it had been trained in AI, and there was some sensing function it had to do, and the thing turned upside down. And the pilot thought something real weird was going on, but there was some orientation of the airplane that made it optimal to do the sensing function. My sense is we need to trust but verify, maybe. I'm a little, I think AI can do a lot of great things, but I have this nightmare that 12-year-olds someday won't be able to do long division on a piece of paper,
Yeah, I would just comment on the security issue. I mean, I think the AI just, is, I mean, you don't even have to think about AI. You can think about chiplets and adding all these chiplets to an interposer, and there are some maybe untrusted chiplets on there, and they have visibility into everything that's happening. And so that needs to be checked. The other one is things like memory consistency models being different between the two. And so you see things like, Spectre and Meltdown, and I mean, it's something that needs more attention, right? Even without AI. And so, and then you add that to the mix, and it's a wide open space.
Can I ask a question? All right, so, and thanks for all the very visionary talks. So my question is about the tool chains. The tool chain, the work that presented by Jeff is actually very visionary in that sense, where that's what completes the big picture. Without those tool chains extending from materials to systems, what we do will remain incomplete. And especially, this is important for different researchers at different levels. When you look at the big picture in different domains, including superconducting computing as well, the tool chains that you need to use are essentially tool chains of tool chains, maybe tool chains of tool chains of tool chains, right? And Jeff showed like a four different levels of tool chains. Like, let's assume a researcher, a student working on materials, and they make a change, a small change in the material property and improvement, and they want to see the higher level effects of that. I mean, what we have, even with completely working and open source tool chains, which pretty much do not exist, like with the full level, right? Even the assumption of those, it will take probably months to coordinate with other researchers and maybe get some idea. My question is, like, are we really like going towards a direction where we have simpler tool chains that is more like that's spanning the entire spectrum, or as much as the levels available, like as much as we can? Are we going towards that direction, or maybe the other way? What do you think about it?
Yeah, so I had a couple things pop in my mind. It would deal with these automated place and route tools, and sometimes even with a simple input of a change, we get a surprising result on how it reacts to you know, a better cell, or it can take the same cell and it can break it apart and route it several different ways, and we just don't have any transparency on it, right? Now, I think that same problem exists through all those type of levels. Is we have full transparency and we have full understanding of all the decisions that these tools are making, and I think the answer is no. So I don't know what can be done to make that a more transparent, more simple process that we could optimize, but yeah, I think there is opportunity.
Okay, any other questions? Maybe I can ask a very brief concluding question as a follow-up to the most recent one on abstractions. So our seeding question was also about abstractions, but there's also this inherent question of the right level of abstractions. Too much abstraction can also be harmful, actually, for design, especially at the system level. Whenever there's a new device, what we do is we try to characterize the potential. And it's usually great. It beats everything, especially on the traditional von Neumann CMOS side. But then when we start considering the practical effect, noise effects, reliability, and actually designing a system using these materials, then we start to see some significant decline in those great performance or energy efficiency numbers. So maybe this is a very mean question, or maybe there's no answer, but what is your take on what is the right level of abstraction?
I'm not exactly sure what the right level is. It may depend on what you're trying to accomplish in your maturation process, but this is being the scenario you set up is being tackled by a few folks. Mike Niemeyer at Notre Dame is trying to do a kind of a holistic from device to systems a model of types, you know, trying to put together a systemology to be able to evaluate if you have an end application, how might you go about putting something together. Sumit Gupta at Purdue's doing something very similar just for neuromorphic applications. And it's hard. It's really, I mean, there's gazillions of variables and propagation of uncertainties that may amplify or not. You know, so I don't think I have a really good answer for you, but it probably is, it it depends on what you want to accomplish. So if you want to, I think weeding out things quickly, if you can get to failure or success faster with some abstractions, and then realize, all right, we need to put more fidelity into carrying a concept forward, that might be the prudent way to go. I don't know if it's a satisfactory answer or not, but it's a good question.
Yeah. I would, I think that's a really important question. I mean, I reason from my software years and think about, that's the way we manage complexity, right? Is having that abstraction in there. And you look at things like the TCP/IP networking stack, and you look at other examples like OpenGL. It just freed up this entire industry to go off and innovate while maintaining some level of compatibility with the applications and all the libraries and things that people had already built. And so it's really important for that reason. But you need the tools that can optimize out those levels of abstraction to get, when you actually get to an implementation, maybe be able to see through that and do some types of optimization and, keep, what's the old joke, right? You solve all performance problems by removing abstraction, and you solve all complexity problems by adding abstraction, right? And so that's been around about as long as computer science. One other note I wanted to mention was the memristors. There was a lot of talk about memristors, and this is where I think we're in an age where some of the technologies might be able to find a niche and start growing in that niche and then improving. And in memristors, about 10 years ago, there was a lot of hype about them replacing DRAM, right? And in fact, some of the memory vendors had announced products that were memristor-based DIMMs that you could put in a system, right? Now, we never saw those, but part of the challenge was just durability and write latencies and power and those types of things. But now if you take those memristors and you put them in a high-energy physics system that maybe need to be reprogrammed once a day, so the durability is not a problem, and then you have a lot of power, you're not that worried about power and things like that, that could be a reasonable niche for those to flourish, right? And so that's where, I think the direction we're moving with heterogeneity makes it a lot more viable for new technologies to have an on-ramp.
All right, anyone wants to add anything else before we conclude the panel?
You need to put like a little tape on the button so we can find it easier. But anyway, no, I think what Mike said kind of reinforced the idea that if you get this little bit of an improvement, and sure it's an improvement in the one case, but once you fan it out through the thousands of complexities, you can either get lost or perhaps in that thousand complexities that bit of efficiency was already solved, right? So I've seen kind of both cases, and so yeah, levels of abstraction. I don't see an answer in that. I think we're always going to have that type of problem. Yeah.
All right. Thank you very much. Any other questions from our audience? All right, let's conclude this panel and thank our distinguished speakers. Thank you very much.